What's up, fam squad? Chucky Hats out here, and welcome back to my Minecraft Let's Play. In yesterday's episode, we went to the end and defeated the Ender Dragon. And now we're back in the overworld, and we need to build our official Minecraft base. So, thus far, we've been kind of living out of this the Fortnite battle bus that I've built here. Very nice, very pleasant. But we're too big. We're too big for that now. We need to move on to bigger, better horizons. So I'm gonna go into the mines, and I'm gonna start getting some materials so we can build a new base. Not again. Not again. Not again. Oh, okay. All right. Okay. To build your base, you must answer this one question. What is a derivative? The understanding of a derivative is all underpinned by the understanding of rate of change. Slope-intercept form is y equals mx plus b, where m stands for slope. This is the average amount the function increases in y per increase in x. Therefore, it can be found by dividing the change in y by the change in x. Finding the slope of a linear function is pretty simple because it is constant. As can be seen in the table of f of x equals 2x plus 1, the y changes by 2 per every 1 increase in x. This is corroborated by the graph. The instantaneous rate of change describes the rate of change at an exact x value. This can be thought of as somewhat as the speed the graph is changing at this exact point. This is simple to find in a linear function as the slope is constant, in this case always 2. This is not so simple for curves, however, as can be seen in the table of values of x squared. There is no constant rate of change, and this makes determining the instantaneous rate of change very difficult. However, the instantaneous rate of change can still be found, or at least approximated, because of a local linearity. As can be seen in the graph of x squared, it begins to look very curvy. However, as we zoom in, the curve begins to more and more resemble a line. Local linearity is predicated on the assumption that if you zoom in far enough on any curve, it will look like a line. The instantaneous rate of change will therefore be the slope of this locally linear segment. The slope of this line will be the same as the line tangent to it, meaning the line that passes through only that one point on the function. Take, for example, x equals 1 when f of x equals x squared. The tangent line in this case is 2x minus 1, as can be seen in the graph. When we zoom in on the point 1, 1, where the two intersect, they are virtually indistinguishable. Finding the slope of the tangent line is the same process as finding the slope of any linear function, and that is to divide the change in y over the change in x. This is stated through the difference quotient. The difference quotient is that the f prime of x equals the f of x plus delta x minus f of x over delta x. Apply this, for example, to the function x squared at point x equals 1. Using the difference quotient, we can see that with a delta x of 1, the slope of the line tangent to x equals 1 is 3. This clearly conflicts with the 2x plus 1 tangent line that we have already identified. What we just made is a secant line, but not quite a tangent line. The difference between a secant line and a tangent line is that a secant line passes through 2 points along the function. This is the way that the difference quotient must work, because it needs 2 points to find the change in y. However, local linearity saves us again. Linear functions don't have this problem because their slopes are constant. So if we apply the difference quotient to a very zoomed in area of the function, it should work just as well. Changing delta x to instead 0.0001, it can be seen that the difference quotient yields a number that is approximately 2. Well, you may not have realized it. What we just did is approximate the derivative of f of 1 when f of x equals x squared. The symbol f prime of x means the derivative of the function f of x in the field of calculus. So derivatives can be found at a single point, and therefore can be extrapolated to fit an entire function. The functions on the right here are the derivatives of their counterpoints on the left. The first function is y equals 2x, as can be seen in the graph of its derivative. Its rate of change remains constant at 2, and we know it will be like this as the function is increasing and therefore has a positive slope at all points, and the rate of change does not change itself, therefore it has to remain constant. However, in x squared, it is not as simple. It decreases before x equals 0, meaning the derivative of those points must be negative, and then increases. Therefore, its derivative is changing and goes from positive to negative at x equals 0, as can be seen in the graph here. To find a more exact value for the derivative of x squared, we can apply the difference quotient. This is represented by the blue line here. This follows 2x almost exactly, meaning that we can say that the derivative of x squared is approximately 2x. Thus far, we have been approximating the derivative, however, we have not yet been able to conclusively prove it. To do this, we would need to set delta x to 0. This, as can be seen, is impossible as we cannot divide by 0. Instead, we use what is called a limit. For example, in the function y equals x times x plus 1 all over x plus 1, we cannot solve for x equals negative 1, because if we did, the denominator would be 0, and as established, we cannot divide by 0. Instead, we ask what the function seems to be infinitely approaching as x equals negative 1, and this is represented in an equation as the term limit. So we can apply this concept to the difference quotient. Because delta x infinitely approaches 0 in this way, the equation will give an exact value for the derivative. This is called the limit definition of the derivative, and note that I replaced delta x with h. In this case, they both mean the same thing. H is just easier to write. So this can be used in very complicated examples, for example, 2 to the x, to show other ways that the limit definition can be used. So as x is in the exponent, we can add delta x, and that must be done inside the exponent. And then from here, we can use the rules of exponents to replace 2 raised to the x plus h with 2 raised to the x times 2 raised to the h. And therefore, now both terms in the numerator both share a greatest common factor of 2 to the x, so we can factor that out. It is known that as a given variable approaches 0, a constant raised to that variable minus 1 all over that variable will approach the natural log of the constant, and therefore by removing 2 to the x from the fraction, we can use this equation to substitute in the natural log of 2 as the second factor. Therefore, the derivative of 2 to the x is 2 to the x times the natural log of 2. Yay, we did it. We did, look at that. I built my base in Minecraft. Let's look inside it. Let's look inside it, shall we? Look, it has a bookcase and giant tree in the middle. What a nice house. Welcome. Thanks for subscribe. Good. That's it. See ya.